Thank you very much, Klaus, for the introduction. Thanks to the organizer for the nice invitation. It's a great pleasure to be here. So today I will introduce the topic of diffusion and mixing in fluids. And I will mainly talk about two models. One is the so-called passive scalar model, and then the Navier-Stokes equations or Euler equations. So I think my talk will overlap a little bit with what Tarek said yesterday, but that's good repetition, I guess. So the two models, one is about passive scalars. So passive scalar is just a scalar function f that depends on time and space. And it is transported by a given vector field, velocity field u. So given u, the divergence of u equals 0. Okay, so it's an incompressible velocity. And there may be some molecular diffusion with diffusivity coefficient nu. And so the equation that I look at is something like this. So this would be my passive scalar equation. So I will initialize with some initial condition, f of 0. And I will consider this equation, well, for positive times. And in the domain D, which will be in R2. OK? So it doesn't really matter for this, but we'll mainly stick to 2D. And so if the boundary of D is non-empty, then we have to put boundary conditions. So it will be Neumann boundary conditions. These are the no flux through the boundary. So the gradient of f dot the normal vector to the boundary is 0. Okay? So physically, right, what we're looking at, we have some domain, which will often be just a periodic box. Okay? And we have some initial concentration F0, so a diode color, right? And we steer it in an assigned way given by u. And we look at how it evolves in time. Okay? And there will be some diffusion, so maybe there will be some steering. So this is a time t equals 0, at times t greater than 0 is something like this. And we look at what happens for t going to infinity, essentially. Okay? So that's the main thing. By the way, if anybody has any question at any point, please feel free to interrupt. Okay? So this is passive because u is not influenced by f in any way. Okay? So there is no feedback of the concentration into the velocity. Now, an active scalar, so the example is the Navier-Stokes equations. This is the second equation that we will look at. And so I'll just write it as Tarek wrote it yesterday. So this is just Euler if it's equal to 0. And I put nu Laplacian of omega. So omega is the vorticity, and u is recovered as the gradient perp of a string function psi, and the Laplacian of psi is equal to omega. And again, I'll have an initial condition and so on. And a lot of the things I will say, they are good for both Navier-Stokes and passive scalars. And I'll make sure that when there is a difference, I will make sure I'll make it known. So in this case, though, let me just say that I don't want to deal with boundaries. So at least when nu is greater than 0. So when nu is positive, the boundary will be empty. Okay. We'll have other lectures about boundaries, so I don't want to interfere with that. So because I don't know how to do much with boundaries in the things I'm going to tell you about. So for Euler, it doesn't really matter. Okay. So when nu is equal to 0, we can deal with boundaries. Okay. Okay. So in 2D, right? So the point is that in 2D, both equations, okay, so this is n is a. Okay. So there is no issues about well-posedness. Okay, so the question, meaning that if you start with a smooth initial datum, you'll have a smooth solution for all times. So the question is really the long-time behavior. Okay, so what happens as t goes to infinity? So that's the question I want to address. So, and I try to claim that if you want to understand what happens for Navier-Stokes, you really have to understand also what happens for passive scalars. So that's why I will mainly talk about passive scalars. So what's a first estimate that we can have? So let's just start with a simple case. Is about just diffusion. Okay, so when I talk about diffusion, so I really want to just look at the energy of this equation and see what happens. So this, it really doesn't matter if I look at passive scalars or Navier-Stokes, okay? But let me just take the torus for now. And I look at solution with 0 average. Okay, so I will assume that the initial datum 0 average initially. And this, by the way, implies that f of t is also 0. Okay, and this is okay for both passive scalar and Navier-Stokes. Okay, so I'll say I'll write f, but omega is the same. You'll see by the computation. Okay, so when we just do the energy, the basic energy estimate for this problem. So what do I mean? We multiply by f, integrate, and integrate by parts. And because I am taking a divergence-free velocity, this term will disappear from the estimate. So the energy estimate is the energy, say, balance is just this. Okay. And well, because I'm looking at mean zero functions, right, I can just use Poincare inequality. So I put lambda 1 as the Poincare constant, which in this case is actually 1, but OK. Less than or equal. OK, so this is just Poincare. And so what I get, right, is that f of t in L2 decays like e to the minus nu, oops, so lambda 1 nu t times its initial datum. Okay, so this is one answer, right? What happens as nu goes to infinity, everything goes to its average, right? So that's what this is saying. Exponentially fast with a rate proportional to nu. That's what I want to really emphasize, rather than it just goes to its average, okay? So let's say that we have what's called the diffusive timescale is proportional to 1 over nu, okay? O of 1 over nu, which is the time at which the solution becomes order 1 in nu, okay? So, but you know, what was the role of u in this estimate, right? Nothing really, right? So if u was 0, we would get exactly the same thing, right? So u didn't play any role in this estimate. So u did not enter in the estimate. I mean, because you know, it's divergence free, so that's why nothing happened. Okay, but you know, this estimate tells you essentially. So if you had to explain this estimate to your 5-year-old cousin, what would you say? So your cousin is like trying to, you know, get the bus to go to school or whatever, and is like drinking his decaf coffee because it's 5-year-old, and with milk, and you're telling him, look, it doesn't matter whether you steer or not, right? Everything will just become cafe latte in at the same speed, right? Whether you steer or not. This is what this estimate tells you, right? Just wait it there, diffusion to act instead of steering. It doesn't matter, right? And the cousin will be a little puzzled, I hope. Okay, so we'll try to just give a better, you know, mathematical explanation to when your cousin goes to university. But for now, that's the same what this is saying. So I want to now just work through an example, and we'll see that, in fact, steering matters, right, as it should. And so that's what I'm going to do now. So I'll just go to a new board. Okay. So steering matters. And so we're just going to look at the Coti flow. So Coti flow means that we're looking at this divergence-free field, y0, and my domain is periodic in x and the whole space in y. Okay? So just because this will allow us to do a lot of computations. So this is a type of flow that is like a parallel flow like this, right? This is y and x. And so you can imagine what happens when I put a concentration here. Okay, say that I start, maybe I should change color. So let's say that I drop my milk here. What happens, the particles above the x-axis will be stretched this way, and below the x-axis will be stretched this way, right? So something like that, right? They will be stretched. And then because I'm periodic in x, I will just wrap around the torus. Okay, that's what happens. And so this is the action of this guy, and the equation becomes somewhat simple in the passive scalar case. So the passive scalar equation becomes just this, y dx, right? That's the transporter. So for Navier-Stokes, what does it mean that I look at the coed flow? It means that I really look at what happens to the vorticity when I'm putting myself near the coed flow. The coed flow, right? So what is, so for Navier-Stokes, is more like sort of a perturbation type setting. So let me just call it U bar now, because so and omega bar is -1. This is a stationary solution to Navier-Stokes, right? You just look at it from the equation. And so what I do, instead of looking at really the whole vorticity omega, okay, I look at perturbation near omega bar, right? So when I talk about Navier-Stokes, most of the time it won't be about the total vorticity, but the perturbation of the vorticity near a steady state. So if I plug in the total vorticity in Navier-Stokes there, right? I mean, this is just, and this is sort of independent of this being exactly the coed flow. We'll look at the equation in general for later. But if I have a stationary solution to Navier-Stokes, okay, I plug in and I want to write now the equation for the perturbation omega, okay? So in this particular case, so what I would have is that I have dt omega plus, then I will have u bar plus u dot grad omega bar plus omega is equal to nu Laplacian of omega plus omega, sorry, omega bar plus omega, right? Stationary, so I don't have that. But even if I had the time-dependent solution, I just put omega bar in here, right? And then I have to use that omega bar satisfies the Navier-Stokes equations. So doing that, it means that u dot grad omega bar plus nu Laplacian of omega bar will go away, right? So let me just say that this term here will just disappear. And also this term here disappears, right? And I'm left with two linear terms in general. And the nonlinear term, u dot grad omega. Okay? Two linear terms because I have a quadratic nonlinearity. But in this case, omega bar is -1, right? So really the gradient of omega bar will disappear. So all I've left is u bar, which is y0, dot the gradient of omega. So this will be just y dx omega. So I have dt omega plus y dx omega equals nu Laplacian of omega, and then I have the nonlinear term. Okay. So which for now I will forget, right? And so I get exactly the same equation. Okay? So of course, then I would want to prove something nonlinear about these equations, okay? So it's not that the results will be the same in the end. But for now, the linearized problem, at least, it is exactly the same. So it doesn't matter what I talk about. Okay, so let's keep f as my variable. And so let's solve this equation, okay? So the setting is that I did is very convenient, the T cross R setting, because I can take a Fourier transform in x and y of this equation. Okay, so let me call, so x will become k, and this will be in z, because x is periodic. And y will become eta in R. Okay, so Fourier transform. So what is the equation in Fourier? So y becomes I eta, and dx becomes ik. Okay, so sorry, y becomes I d eta, right? It's derivative on the Fourier side. So I call, so f hat is now a function of tk eta, right? Satisfies dtf hat plus k I times I is minus 1, right? So f hat is equal to minus nu k square plus eta square f hat. Okay, so that's the equation, and I can solve it. So you see that without the nu, this is really just transport equation, the one that you learned the first day in PD1, right? Constant drift, right? Then there is some diffusion here. So let's just undo the transport part. What do I mean by that? So let me just define a new function, which is f hat times t at k eta minus kt. And well, I can also just undo the x diffusion. So let me just do this. So this shift just takes care of this, right? In Fourier. So let's compute the equation for g. So what is dt of g? If I did the signs correctly, okay? So I get dtf hat minus k d eta f hat. And then I can hit here, which I get exactly plus nu k squared f hat times e to the nu k squared t. Okay, seems that the signs are correct. And then it's equal to the remaining term, right? But not at eta, it's at eta minus kt, okay? So this is just equals eta minus kt squared, nu squared. And then I get, well, f hat times e to the minus, e to the nu k squared t, so I just put g, right? So in dtg is just nu eta minus kt square g. There is a minus. It better be dissipation. Okay, so that's it. So now these I can solve by just integrating, right? So g of t k eta is just e to the minus nu. Sorry. So it's just g0, which is exactly f0 hat at k eta, e to the minus nu, the integral from 0 to t of eta minus k tau squared d tau. So if I go back to f hat, okay, so you see when I go back to f hat, I'm going to have to multiply by this factor. You see, this factor really doesn't matter if for now, right? If I didn't have this factor, it would be exactly the same. But OK, I'll have that. And then I have this, OK, here. And so I want to reshift the coordinates, OK? So I want to really write f hat of tk eta is equal to f0 hat. Now, because I'm shifting, I get eta plus kt. OK, I'm shifting back this guy. And here I also get some shift. So I get e to the minus nu squared t minus nu integral from 0 to t of eta minus k tau minus t square d tau. So this is just an the exact solution of the equation, right? I solved it exactly. Let me just change variables here. I'll just write it in blue here. So if I just redefine this, I can just put this is equal to s and integrate in ds. And nothing else changes, OK? So everything stays. Well, I guess this becomes a plus. So this is minus s for me. Then nothing really changes. OK, so what can we get from this formula? Where is the? So you should be just, you see, there we are integrating tau squared, basically, or s squared, right? So it will become cubed, right? So t cubed, which is a very fast decay, right? It's so that's what I'm aiming at. So if we rewrite, so let me just look at that integral. So it's the integral from 0 to t of eta plus ks s, right? It's the same thing. So if I compute it, right, this is just t times eta square plus k eta t plus k square t square over 3. Okay, please correct me if I'm wrong, but I memorized it. I don't know how to do this. So so let me complete the square here, right? Now this is really, so here I get eta plus kt over 2 squared. And then I get this 1/3 of this minus 1/4 of this from here, which is 1/12 of that. Okay, which is greater than or equal k squared t cubed over 12. Okay, so that means that I can just bound that pointwise, right, like this. So f hat at tk eta is less than or equal f0 hat at k eta plus kt times e to the minus nu k squared t, e to the minus nu over 12 k squared t cubed. Right? That's, I'm just putting this bound right there. Okay, so this is way faster decay than the diffusion, right? This nu t, well, here we have nu t cubed. Okay, so that's what's happening here. So let me just retranslate this into estimates in real variables. Let me see if I'm forgetting something. So maybe I'll just put a proposition here. So when is this estimate good, really? You see, I'm throwing away all the y information, right? Because eta, I just threw everything away. So here, if k is equal to 0, there is nothing, right? But if k is equal to 0, even from the equation up there, here, if k is equal to 0, you see that the transport part is not there at all. So you know, you wouldn't see any steering, if you like, right? So k equals 0 means that I'm going to remove the x average out of my solution. So let me just define f nec as sorry maybe let's f. So let me just say like this. So suppose the initial datum, so the x average of the initial datum is 0. Okay, which means that in all I'm saying, and this will be something that will be always true basically for shear flows, okay, for everything I say. Suppose that you don't have any x average, okay? So this translates into Fourier that k can never be 0, okay? Then something that you get from here is that f of t in L2 will decay like initial datum L2 times e to the minus nu over 12 t cubed, right, for all times. Okay, so this is an example of what I call enhanced diffusion. Maybe it deserves a better spot than the last. So basically, there is a new time scale which is O of, so what is the time at which the solution becomes order 1 in nu now is 1 over nu to the 1/3. And so this is an example of enhanced diffusion. I'll give you a definition later, but I just want to introduce the concept as by an example. Okay. So there is a new time scale, which is really what we should focus on. The fact that there is a super exponential decay is kind of very particular to this example. Okay. So we'll not focus on the super exponential decay, but let's focus on times. Okay. So time scale 1 over nu to the 1/3. So this is saying that if you steer, it actually in a quantitative way, things will homogenize faster, right? At this time, as long as you drop your milk not in the k equals 0 frequency, right? That's your initial condition. So in a shear flow, it means that if you just put horizontal stripes of your milk, right, you'll never do anything because you never mix in that direction. Okay, but otherwise, everything will mix very fast. Okay. So what's really happening here, though, is so where does this extra decay come from, right? It doesn't come from something, diffusive per se, but it comes from this fact, basically. So it comes from, these shifts, right? So these shifts here are what make the diffusion Fourier symbol here time dependent, right? And that's what gives you, when you integrate, that's what gives you the cubed instead of just linear power. Okay? So that is an effect. So if nu is equal to 0, right, this is just an effect of the steering. This is a shift of frequencies here. Okay? So let's say just a few remarks. So this is, I guess, the first remark. But so for nu equals 0 and k not 0, okay, there is some transfer of information to high frequencies. So it's not true anymore that your solution is concentrated in the first frequency. Essentially, this is what you're doing here. Here you're saying, oh, worst case scenario, my solution is all in the first frequency, right? That's what using Poincare inequality does. So, okay, that's, but if you think of steering, you really create small scales. And so your solution should develop gradients, right? We saw yesterday with Tarek that gradients may grow linearly. That's exactly the case here, in fact. And therefore, you would expect to have sort of an enhanced Poincare inequality in a sense, right? A better one. And in this case, it's sort of like the Poincare constant was t squared, not lambda 1, right? If you put t squared there, that you integrate, you get t cubed, right? That's what it looks like. And t squared is exactly the growth of gradient of f squared, right? It grows gradients grow linearly, so you have a kind of a t squared there. This is just heuristics, but this is so there is something called inviscid mixing. So, which is the fact that you have f hat of t k eta is f0 hat of k eta plus kt. Okay, so things go to high frequency in y, right? And so of course, if you measure mixing just in L2, what are you going to get? Transport equation, L2 norm is going to be conserved, right? So of course, this is not the right way to just measure any mixing here. But if you think about what it means to create small scales and so on, well, you're really sort of creating an averaging effect, right? So an averaging effect is more associated to weak convergence in L2 rather than strong convergence. So you're never going to see anything in strong norms, right? But let's try to compute the h-1 norm of the solution, right? So what happens if you compute the h-1 norm of the solution? So let me just give you an example. This is an example of an inviscid mixing estimate. So what does it mean that I compute the h-1 norm? It means that I'm going to look at f hat k of t k eta, okay, squared. and I divide by k squared plus eta squared. And then I integrate in eta and sum in k, right? That's k not 0. OK, let me just do a pointwise computation. So I just substitute this here. Maybe we can just integrate in eta for now, but it doesn't. It's really a pointwise thing. So eta plus kt. OK, let's multiply and divide by the same thing. So let me just write it maybe like this. So k squared plus eta squared times k squared plus eta minus eta plus kt squared. And then I multiply plus kt. Eta plus kt squared, the eta. Plus k squared, sorry. I didn't do anything. But now you see that what is this term looking like? OK, if eta is far from kt, let's say bigger than 2 kt and smaller than kt over 2, or something like that, well, then this term is like 1 over kt squared, right? If I'm far away. If I'm close to minus kt, right? If eta is close to minus kt, then this term is just, you can just, it doesn't tell you anything. But eta is close to minus kt. So this term will tell you 1 over k squared t squared, right? So all I'm saying here is that pointwise, this guy is bounded by some constant times. So I'll use the brackets to say asymptotically in time is like kt. Okay, so that's just equal to kt for large t and equal to 1 for small t. So this term is like bounded by this guy. And well, this is exactly, if you now revert back to the original variables, really this is just the, I mean, this is just the H1 norm, right, of the datum. So let me also then forget about the k. So I get f0 in H1. Let's say in both variables. You don't really have to pay any derivatives in x, but for the sake of so the mixing H1. Oh, okay. This is the bound, but I was about to write. So the mixing estimate is but squared. That's so the mixing estimate is that f of t in h minus 1, now without the square, is less than or equal 1 over t f0 in h1. OK? So just checking the time, sorry. OK. OK, in fact, one here is kind of arbitrary. I can put s here. I'll get s here and s here. OK? So if you do it in h minus s, right, you still get. So in particular, you have to pay s derivative to have a mixing estimate of order 1 over t to the s. Okay, that's. Any questions so far? H minus 1 was actually introduced as a measure of mixing in a paper by Charlie Doring and others. And in 2D, it sort of makes sense because h minus 1 is exactly a dimension of length. Okay, so if you're thinking that your scalar goes to smaller and smaller spatial scales, maybe it's good to be dimensionally correct and measure a length scale of the solution, okay, in a sense. But mathematically here, at least, it doesn't really matter. Any S norm is okay. But the point is that you have to pay derivatives to get decay, okay? So you will not just get decay for free. Okay, so by the way, maybe something to think about as an exercise. This is the same as saying that the Fourier transform, f of t converges weakly to 0 in L2. 0 being the x average in this case. Okay, so but in general, right, if the h minus 1 norm of a solution of transport equation like this goes to 0, is equivalent to say that you have weak convergence to 0 of your solution. So again, if you think about averaging, that's very consistent. Okay, so for this case, in fact, you can get, see, because you have the solution, really, you can get anything you like from this example. And in particular, you can get some good estimate for nu positive even mixing, okay? So let's say that you can get mixing plus enhanced dissipation, or enhanced diffusion, which means that really what you can get is that f of t in h minus s is less than or equal f0 in hs over t to the s e to the minus t cubed. Okay, so and this is true for any s greater than or equal to 0, right? The equal to 0 case, we saw it before. Okay. Also, some of these, you know, are things that we know how to do only for coet. Some of these things, and you know, I'll be happy to answer a question about that. But so obtaining these for more general flows is much harder. Okay, so you can get these two things separate, mixing or enhanced diffusion. Getting them together, it's a little harder. Okay.
Is there a theoretical upper bound on how much better we can get on the time scale, best time scale possible?
Yeah. This is the best say for any autonomous 2D velocity field. Nu to the 1/3, nu to the minus 1/3 is the best you can. This will be lecture 3 or something. So I will talk about it. But yes, so I mean, but you can believe that all of this is sharp, right? So I'm just giving you upper bounds, but I mean, I'm using the solution. Yes?
Yeah, I have a question. Is it possible to construct a lower bound for these norms?
So I can tell you that, so it depends. So for this estimate, maybe, I don't know, but I'm sure that if you work out with the, you know, exact solution, you pick an initial datum, because in the end, for a lower bound, what you want is to say, oh, there is an initial datum that doesn't get better than this or something, right? What I'll show you is that the relation between nu and t cannot be improved in general. Okay, there are no initial data that will enhance dissipate faster or mix faster than that. Okay, that's what you can say. Other questions?
I don't understand why f is going to 0. I would suggest that it goes to the average.
Yeah. Everything is so okay. Everything is 0x average. So particularly 0 average. But yes, it's an averaging thing, so it goes to its average. I just set it equal to 0 because it's a conserved thing. Yes. Otherwise, just write f minus its x average in this case. Yeah. Okay. Okay, so before going to more general stuff, so what does it mean this for Navier-Stokes, right? So, or Euler. So for Euler, so nu equals 0 in Navier-Stokes, right? So we saw that the linearized equation is exactly the same, right? So all I wrote here, you put omega instead of f, everything is true. But omega is the perturbation, right? So what this is saying for Euler is that solution that start near the coed flow will converge rapidly to the coed flow. Rapidly in the sense more, I mean, faster than just the diffusive decay that you would maybe naively expect, right? So this is what it's saying. So historically, however, things are measured in a little bit of a different way than h-1. So one thing that you would get, right? Remember that Laplacian of psi is equal to omega. So if I measure psi in L2, it's like doing an h-2 estimate for omega, okay? So one estimate that we definitely get is that in L2 is like putting s equal 2 in this estimate. And of course, for Navier-Stokes is the same. So this estimate is really true. But let me focus on. So again, you pay two derivatives, and you decay like t squared, right? So in general, when you want to prove something about Euler, you go to the stream function. And what you do in the end is prove what's called an implicit damping estimate. So what is implicit damping? By the way, this computation was essentially known to Kelvin in 1887. Okay, so I'm not claiming any novelty here. Okay, so what you would like to say, so what are good integrated quantities, right? So you have to think that h minus s norms, right, are sort of integrated quantity. That's why they decay thanks to some sort of averaging. So something that is -1 derivatives of the vorticity is the velocity, right, in Navier-Stokes or Euler. So one way that it has been these questions have been looked at is looking at the decay of the velocity field near, say, the coed flow. So the velocity field of the perturbation, like the first component, is minus dy psi, and the second component is dx psi. Okay. So what can we get for this? Okay. So again, just to write it in Fourier, right? So U1 in Fourier is going to be minus I eta over k squared plus eta squared, the Laplacian inverse of omega hat. Okay, which, so this is really square root of k squared plus eta squared. Okay. And so in the end, you see, you do exactly the same computation I did essentially for the h-1 norm of f here, right? You have exactly the same symbol down there. Omega is just shifted by mixing. So in the end, this will tell you that U1 in L2 minus its x average in L2 will decay like 1 over t. And here there is some norm of the initial vorticity. Let's say H1 because I'm doing exactly like that. Okay, and the second component, well, the second component doesn't have an x average, right? Because it's a dx or something, and we're periodic in x, so there is no need to remove the x average. U2 in L2, well, instead of having eta, you would have k here, but k doesn't really get shifted, right? Because it's just the dx of something satisfies the same equation as that something in all of this business for now. So this really decays exactly like the stream function, so 1 over t squared by paying, say, 2 derivatives. Okay. So this is an example of, say, linear implicit damping. So it has typically been measured in terms of decay of the velocity field near perturbations, right? And this has nothing to do with diffusion, right? It's only about the mixing of the vorticity by the quiet flow. Okay. If you want to add dissipation, again, it's just a pointwise thing, so e to the minus nu t cubed here and here. Okay. Everything will decay like that. Okay, so so maybe I should name. So linear here stands for the fact that I'm looking at the linearized Euler, okay, near coet. So linear is linearized Euler. So maybe I should just say for the nonlinear problem, so which I'm not going to talk about in this course. So for the nonlinear implicit damping, the result would read something like that, very loosely speaking, is that let now omega 0 in some space is smaller than epsilon, small, okay, where x is some infinite regularity, so kind of almost analytic, so Gevrey 2-ish. Okay, you can, I mean, I guess you can get exactly to 2, in fact. So but something that, so the initial perturbation now near the coet flow is of infinite regularity, is small, okay? Then, same estimate, then the nonlinear solution satisfies implicit damping. Okay, which means an estimate of this type. Okay, so even at the nonlinear level, you get this decay. And this is a result by Bedrosian and Masmoudi in maybe 2013, or this is definitely wrong. So the statement is also much longer, but let me just trivialize it like that. Hopefully Jacob is not watching. It's early in California. So. Okay. So, but this meant not to erase this term here that I'm erasing right now. Okay. So, okay. So. So I'm going to start now with some more general concepts, but if you have questions, maybe now it's a good time to ask. before I get into slightly more general stuff. All good? Okay, so let's just give a formal definition of mixing and enhanced dissipation, okay? So, and let's think of so general concepts. And let's think of the passive scalar equation for now. Everything can be sort of rephrased for Euler and Navier-Stokes as long as you think of a perturbation near a steady state, okay? So let me just give you two definitions. So definition one is about mixing. Or when I say mixing, I always mean implicit mixing, okay? So so you can say that now a vector field U, okay? Remember really the first. So U is mixing at rate gamma of t, which gamma of t should be like something that is a continuous function, is a rate function, right? So it's something that goes to 0 as time goes to infinity, and it's decreasing or something like that. Okay, if for every initial datum in H1, f of t in H minus 1 is less than or equal 1 over gamma of t f0 in H1. Okay, if we believe that the behavior in the quiet flow is sort of true for a lot of gamma is going gamma of t. Just of course. So I'm thinking of gamma of t. Gamma of t is like 1 over t to some power, or gamma of t maybe is exponential of t to some power, or something like that. You know, like did I? Yes. Okay. So either algebraic mixing or exponential, super exponential mixing, something like that, right? So those are. So
U is time dependent.
U for now. I mean, I will mostly look at time independent, but it can be time dependent, whatever I want. If it's time dependent, okay, you have to maybe think that you cannot really just say at time t equals 0, so you want to start at time tau and have gamma of t minus tau or something like that. Yeah.
Do we need like f to be 0 on streamlines?
Well, for now, this is just a definition, right? So it may be empty. No, but of course, it's a good point, actually. When I say for every initial datum in H1, I lost. For every F0 in H1, you know, excluding the stupid data like the x average of a datum that doesn't do anything, okay? So, of course, those will never be mixed if you are trying to mix with a shear flow, right? Or if you're in 2D, so let me just remark this. So, say if U is the gradient perp of a psi, okay, so it's a Hamiltonian type thing, then F0 is has 0 average on streamlines. Streamlines. Okay. In general, F0, so F0 has 0 average in all the variables, let's say. At least that. See, because if you have a time-dependent flow, they don't care about, you don't really have a streamline. So you have a time-dependent stream function, if you like. So yes, in general, you have to do this. Okay. So the other concept is enhanced dissipation. Yeah. Yeah. Yeah, of course. Yeah. You can just subtract. I mean, basically, what we're saying here is that the operator u dot grad may have some kernel, right? So let me just, so u dot grad may have kernel, okay, for shear flows, right? For coet y dx, what is the kernel is all f of y, meaning just functions of y, right? All functions of y are in the kernel. So the functions of y will never see anything, but what are functions of y? Functions of y are just x averages of functions of x and y, right? So the projection, what I'm saying is that this estimate should be true if you project out of the kernel, okay? So when you say, in this case, the kernel is exact, so the projection onto the kernel is the average on streamlines in this case. And I just want to subtract that out, okay? In general, it can be whatever it is. I don't want to deal with the kernel, because the kernel will just not see anything there, okay? So that's the remark here. So for enhanced dissipation, we say u, so let's say enhanced this is for nu positive. So u is dissipation enhancing at rate lambda of nu with this property that nu over lambda of nu is to 0 if for every, so I should put it in red also because this is for every in this sense, okay? So for every f0 in L2, f of t in L2 is less than or equal e to the minus lambda nu t f0 in L2. Okay? So what does this condition say about the rate? It's just saying that lambda of nu is much bigger than nu, you know, as nu for nu small. Okay? So again, here the examples are lambda of nu, maybe nu to some power q for q between 0 and 1. Or lambda of nu can be, maybe there is a constant here, but let me just think about the dependence on nu. Or say 1 over log nu to the q, let's say. So these are two things that one can have in mind, okay? Okay, so coet is q equal 1/3 in the first case, right? That's what I was saying. Okay. So in general, it's really hard to, if you give me a U, you know, the goal is determine gamma and determine lambda, right? So that's a question, which is pretty hard, okay? So in general. So just to give you, so I'll give you some results. But so what I'm doing here, so I have my time scales, right? So there is a long time scale that is 1 over nu. That's corresponding to diffusion, right? And then there are maybe these intermediate time scales, 1 over nu to the q, and so it's 1 over the rates, right? So these are the enhanced diffusion. And then there is maybe a time scale of order 1, which is sort of the mixing time scale. But it's, you know, this definition makes sense also for q equals 0 here, which is an extremely fast dissipation, right? So it's a time scale of order 1, and this is sometimes called anomalous dissipation. Okay, it's something that happens really at time scale of order 1. Okay, so reasoning in terms of time scales is like, okay, how fast do I homogenize, you know, and are those time scales sharp or not? So the rest of today and tomorrow, I will try to prove a more general result than Coti, just giving you basically 2 different techniques to prove mixing estimates and enhanced dissipation estimates. Okay, so this will cover both Navier-Stokes and passive scalars. Navier-Stokes only in some cases, but okay. So how am I doing here? Okay, 15 minutes. So let me just tell you some results. So which is what we're going to focus on. So we're going to just look at general shear flows. So when u is just a v of y 0, and v is regular, okay, smooth, possibly with critical points. So with critical points of order at most n and natural number. Okay, so which means that if you think of v as having say a critical point at y is equal to 0, you should think of something like y to the n. So if n is equal to 1, there's no critical point, okay? So that's my convention. N equal 1 means you're just monotone, you're just like Coti, so there's no critical point, but you can be, I don't know, parabola or whatever. So then, gamma of t is 1 over t to the 1 over n. And lambda of nu is nu to the n over n plus 2. Okay? So, and this means really that these are sharp, okay? So you cannot improve this rate, okay? So in particular, you see that the flatter the critical points, right, the bigger the n, the slower the mixing, and slower the enhanced dissipation, right? So this is some exponent between 0 and 1, but it goes to 1 as n goes to infinity, right? And this goes to 0 as n goes to infinity. Okay. Actually, it does, but it's a little bit different, the statement. So, okay, if you take a C alpha shear, then you put alpha here. But it's not as general. It's a little bit more complicated. So it's not really true, in fact, that the gamma is. So generically is like 1 over t to the 1 over alpha. So the rougher, the faster the mixing. But with Klaus and Maria Colombo, we have an example which actually you have a C alpha shear, but it cannot be improved to more than 1 over t. So it's a bit. But this one will be improved in that example. So it's a bit more complicated.
Why is it L or it can be some bound?
So in this case, okay, I should say this is for passive scalars. And so the domains, one can just do T2. I always need periodic in one direction, okay? So, but something like this, and this you put Neumann boundary condition here. Yeah. So this was my first postdoc project, actually. So I did this with Jacob Bedrosian. But then there has been some improvements or refinements by Thierry, by Dallas, Albritton, Raj, Vicky, and Matt Novak. And we also have something with Thierry, but let's say all the names are. So you can do also fractional diffusion. Right now you can do whatever you want essentially with shear flows. If you think about the Coet example, whether you have diffusion or fractional diffusion, it doesn't matter, right? It's just a change in the symbol, but you have the exact solution in that case as well, right? So nothing really matters. So. So this is about 2015, I think, or yeah, 2015. Okay, so in let's see if in 10 minutes. For the log, right. For the log, you have so. The idea is that, so I guess I won't have too much time. So let me answer you in 2 minutes. Let me tell you what are some results for Navier-Stokes, and then I'll answer your question. But it's a good question. So shear flows, you won't be able to get past, at least in the regular case, you won't be able to get past the algebraic decay, okay? And this type of, so for Navier-Stokes or Euler, so there are too many examples. So, well, we know Coet. So what is the linearized equation near a general shear flow? So remember, you have this term will be there, but then the other term coming from the quadratic nonlinearity vanishes in Coet, but not in general, okay? In general, it involves the second derivative of the shear and the stream function, which I'm just going to write as Laplacian inverse of omega. So I just have something only in omega, okay? So this is the linearized Navier-Stokes. You see, for Coet, that term is not there. Okay, v second is 0. So how do you deal with this term? We'll see an example, but there are not many good ways to deal with this term in terms at least of the questions that I'm looking at. So for coet or monotone, you still have gamma of t is like 1 over t, and lambda of nu is like nu to the 1/3. And these can be characterized a little better in terms of implicit damping and so on. So the results that I stated is really for coet. And then we know how to do it for, so this is on t cross r or on t cross 0, 1. V of y is y squared, so the Poiseuille flow. So gamma of t, and this is just at the linearized level. So it's still 1 over t, okay? Which is not, consistent, if you like, with this rate, okay? So, and gamma of t, when I say gamma of t, I mean nu equals 0, so for Euler, okay? So you see, you would expect, because you have a simple critical point, that n is equal to 2, so you have 1 over square root of t. This is what would happen if I didn't have this. But with this, actually, it produces some nice, essentially, cancellations. So you get 1 over t decay. And lambda nu is nu to 1/2. Instead, like n equal 2 here. Okay, so passive scalars here. So so basically, this is something I did with Tarek and Klaus, and this I'll show it the next lecture, hopefully. And this I'll also show the next lecture. And then there is another case, which is, so this is on t cross r. Maybe I should be just, and on t2, there is sine of y. But OK, let me just put maybe t2. OK, let's. So this is also 1 over t. So again, you have an improvement due to this sort of non-local perturbation of the transport term. OK, but this is still 1 over nu to the 1/2. Now, I don't have a proof for Navier-Stokes that the 1/2 here is sharp, but I do have a proof that the 1/2 here is sharp. Okay, so we'll go about. So this was done by a group at Peking University, Wei Zheng and Zhao, and also by Maikawa, Masmoudi, and Slim Ibrahim. So some parts of these maybe, or or all of those. They're way more involved results. So to answer Anne's question, let me just say that I'll just state a result which I won't really prove, but you can prove. So maybe another theorem. So assume U is mixing at rate gamma of t. And here U just have to be Lipschitz in space. But it can be time dependent. It doesn't really, it also applies to some cases of linearized Navier-Stokes, so it's a more abstract result than that. So if gamma of t is 1 over t to the p, then lambda, so, and by this I should put really is less, if you mix at least at rate 1 over t to the p, then lambda nu is greater than or equal nu to the p over p plus 2. I actually, no. I think it's, I don't remember. Yeah, 2, okay. And if gamma of t is like e to the minus t to the p, then lambda nu is greater than or equal 1 over log nu to the 2 over p. Yes. So this is something I did with Tarek and Matias Delgadino. We just call each other by names. So, except myself, I guess. I didn't call myself. Sorry. But you see, at least this is saying if you want to get the log nu thing, you just have to give me a super exponential mixer, which, OK, it's very hard, right? So first of all, about this result, so this is just a quantitative way to say mixing implies enhanced dissipation. Right? That's all it says. Now, if you ask me whether the relations between these exponent p's and these exponents here is sharp, the answer is I don't know, because this is a result that is general and it applies in very abstract way. But if you ask me, OK, if you have a shear flow, it doesn't seem to be sharp. Like if p is equal to 1, then you get nu to the 2/3 instead of nu to the 1/3, which is worse than that. OK, so what is believed, I mean, what is true in some instances is that, be just a remark, is that if gamma of t is exponential, then lambda nu is 1 over log nu. Okay, so exponential mixing goes with log nu. Okay, Tarek has just done a nice example of a time-dependent flow that you have to alternate shear flows in 2 directions. So, you know, otherwise you have to go to multi-dimensions if you want something time-independent, like you take an Anosov flow. This will be exponentially mixing. Our result tells you 1 over log nu squared automatically as a black box, which is not quite 1 over log nu, but it's still like, but it should be 1 over log nu even for Anosov flows. Or in 2D you have to go time dependent, but typically you really have to prove it by hand. Like there is not really a black box that tells you, OK, just you have some mixing, you'll get enhanced dissipation automatically at the optimal rate, right? This would be hard. Yes.
I missed the last remark. So you mean this is true for any?
No. Sorry, no. This is not a theorem. Should imply. Let me erase. Should imply. OK. But it is, you know, we can't really prove something like that as of now. But there are examples of exponential mixer that also enhance dissipate at this time scale. So that's OK. I think I'll stop here for today.